Well, let's take a look at what we got here. Photoelectric effect. So the photoelectric effect is this area at which we will see and explain on the next slide. Little connection between energy of photons, these are the little packets of light that are released, and the color of wavelength we sense with either our eyes that we see on a daily basis or with machines that we use in order to understand chemistry deeper. You want to get used to using these concepts in order to be able to do some simple calculations now that you can use your calculator. We've got the speed of light, which is on your reference sheet. We've got wavelength, often needs to be nanometers, but meters for calcs. So that'll be times 10 to the negative ninth is nanometers. And then frequency is hertz, just a number. We have lambda and nu. So I might say these, lambda and nu. Lambda is the A looking one, nu is the V looking one. So energy is related to frequency. We talked about that as frequency increases, so does energy. And this is the way it gets to. So H is Planck's constant. What this really means is that for each hertz, for each time you have a wave, the lowest amount of energy that can be delivered is 6.626 times 10 to the negative 34th joules. Think of it as a little step. So for us, on our huge macroscopic size, we don't see these little divisions of energy. But in the atomic world, this is the only multiples you can have of energy. So you can't have 7.6 times 10 to the negative 34th. It can only be multiples of this. And that's where the idea of frequency comes in. The higher the frequency, the more energy, which results in a shorter wavelength. So get used to being able to be comfortable with these calculations. You're going to have at least one on your AP test. So photoelectric effect, I mentioned it. Why does it occur this way? So light was shown onto a metal. Only a certain wavelength or frequency excited the electron off, regardless of intensity. So you might say, oh, what are these terms, intensity? So intensity is thinking about it as the idea of how many waves you have hitting something. So if I have one wave hitting the metal, low intensity, five waves hitting the metal, higher intensity. But that just means the number of those, right? So the idea is that needed to have a certain amount of energy, not an amount. This differs from our macroscopic world because if I wanted to push a box across the classroom and I couldn't do it, if my brother who's got the same strength as me helped, we could do it. But that's not what this is implying. This implies that there needs to be something pushing it with an amount of energy highest. So you could have 40 people push that box of all the same strength, it won't budge. But then you could have one person of this minimum amount of force come in and boom, push the box easily. This is very different than what we see in the macroscopic world. Einstein proposed these things of photons or quantum, same ideas, these little increments or packets that are able to push out. You essentially need enough energy to force out that binding electron force. Again, very different, very different than what we normally think, but this allows us to devise concepts for testing. All right, so we'll come back and finish off with Beer's-Lambert law, and I hope to see you soon. Take care.